Okay, welcome everybody. I'm going to go ahead and get started. It's a minute till 4. That's close enough, but we've got a ton of stuff to do. Tonight's topic is recursion, but we've got a lot of things to do before that. I want to start by going over exam 2. After I do that, project 2 is out. It was available this weekend. Your design documents due next Monday, the 20th. The actual project is due the 27th, so I want to spend some time talking about it. The next line is a lie. Lab 8 will be released tonight. It was released 15 minutes ago. It's due Thursday before midnight. I want to talk briefly about it. It's on recursion. Homework 6. The last homework is also on recursion. I'm not going to put homework 6 out until next week. I'll put it out on the 20th. It'll be due on the 27th. So the advice is get a good start on project 2 so you don't have both the things hanging over you the last time. This is the last homework. And then I'm going to talk about some other stuff, but I do want to get going. So first, on the test, as I said, I put a message out on Slack. In general, I was very pleased. There are 22 of you in class. Exam 2 was worth 125 points. So 125 was maximum possible score. So if you just do the math with no curve, and I'll implement a curve at the end of the semester if at all, but with no curve, 90% in A was 112.5. There were 7 of those. 80% was 100 points, was a B. There were 8 of those. So 7 A's, 8 B's. Of the other 7, most of them were in the 90s. So most of them were pretty borderline B. So if your score was 95, 96, don't be concerned. That's not bad. There are a couple of people who I have talked to already. We need to pull some grades up. As I mentioned earlier, I don't want you to stress out about grades and losing scholarships and things like this. I do need you to try. You have to try, do your best. The grades will take care of themselves, but I do need you to try. So let's go through the test fairly quickly. The first question, the method you'd use to remove white space at the end of a string is R-strip, right strip. I think pretty much everybody got that question. Second one, when developing a complex program, involving numerous functions, what's the best design to use? Write the entire program at once, then test the whole shebang at once and hope like heck it works. And when it crashes, start over because you have no clue what the error is, or test each function as you go. We've said that a bunch of times. We will continue to say it. I don't think anybody missed it. Okay. The Python join method is a way of combining the elements of a list into a single string. That is true. It's the opposite of split. Split takes a string, puts it into a list. Join takes a list, puts it into a string. If you don't include a return statement in your project or in your function, the answer is by default, the value none is returned. So it's not true that it's no values. There is a value. It is that value none. 5, what data types have we studied that are mutable? Lists and dictionaries. Of the types we've studied, lists and dictionaries are mutable. The rest are all immutable that we've studied. Suppose A is a one-dimensional list. Now, I said that so we didn't have to go into 2Ds, and those are different. But 1D, the assignment B equals list of A creates a deep copy of A, and modifications to B will not cause modifications to A. That is true. Had A been a 2-dimensional list, it's a little bit more complicated, but for 1D, this is a deep copy, and we're good to go. 7, if string A is Purdue and the string B is Louisiana State, and I slice for A from 0, 1, 2, and 3. That's what the :4 means. And B, I take B from the 10th character to the end. Which of the following? It gives you the first one. That's the answer to that multiple choice. 8. Given this dictionary definition, what's the result of print dogs.keys? Now, I realize we rushed through this on Monday afternoon, so a number of you missed it because of that. I apologize. It's okay. We did cover it. You do need to know it. The keys method gives you a list of the keys in the dictionary. So the first answer, 1, Lassie, 4.2, and George are the keys in the dictionary. So you just get a list of the keys in the dictionary is what the keys does. Values gives you the values in the dictionary. So 9, the result of print dogs.get pepper -1. Okay, from last Monday's lecture, the get method is resilient to errors in that if you try to get a key which is not there, and Pepper is not in the list, he was from too long ago, the second value in the get statement says what you return instead. So since Pepper's not in the list, it would return the second value in the get statement -1. Okay. And then the last one is also on dictionaries. How do you add a key with a value mixed breed as the first element in the dictionary? That was a little subtle, but the key there was the first element. You cannot enter something as the first element. The dictionary is just unordered. Okay. The dictionary is unordered. You can't guarantee it goes in first. You can insert it, but you don't know where it gets inserted. So most people did pretty well on the multiple choice, except for I realize a bunch of the questions were things we covered sort of in a rush Monday, but you had the slides and it was an open book test. So just go back and look at it. It's not a big issue. Make sure you understand dictionaries. Identify 5 errors in the following Python. Now, you should remember that it's not limited to syntax errors. Things that are cause the program to function wrong are also errors. So going through here, the very first thing is in line 1, the function definition, there is no colon. There needs to be a colon right here at the end of line 1. List of keys is fine. For key in D dot keys, again, this is something we just covered Monday, but the keys method, that is a correct, if D is a dictionary, and we'll double check that it is, this is valid, so this is not an error. Okay. List of keys is a list, append key, and return list of keys. The next method, get values, also takes D as a dictionary. Return D dot values is fine. If name equals __ main, that's fine. Cats, we're defining a dictionary. However, we've got an error right here. This is a semicolon, and it should be a comma. So that's an error right here in line 9. That semicolon should be a comma. And the next thing is, this is a dictionary. It starts with a curly bracket. This is a square bracket at the end. So that is an error. These must match. If you told me that this should also be a square bracket as an error, then that's a problem because we have a dictionary, not a list, and it's not a valid list. So depending on what else you told me was wrong, if you said the first one should have been square, I gave you credit or not. The easiest way to fix this is just turn this last one into a curly. While length of cats of keys, this is a problem in so many ways. This is going to be an infinite loop, right? Because length of cats dot keys, there is 1, 2, 3, 4, 5 keys in this. So length of cats keys is 5. So this just says while 5. That's an infinite loop. It's never going to end, and so that's a problem. Okay. List of cats equals get keys cats. It is a dictionary, so this means we're passing to the arguments and parameters to the dictionary. That's okay. Print remaining cats, get values of cats. We've got a problem in that we're never. We're going to have some issues. Let me be clear here. Okay, so this is an error because it leads to an infinite loop. This is okay. This is okay. Cats.pop list of cats sub 0 will actually be okay, and print program finished there was another error in there I'm missing. Hang on a second. There's an error in there. One thing I did point out to a number of people in a return statement, these parentheses, for instance, in this return statement, the parentheses are optional in a return statement. You do not have to have them. This would be fine if I said return space lists of keys, no parents, but it does work with the parents. So the parents were not syntax errors. That was, like I said, that's an optional value. It's not a problem. I think that was it. If I missed one, somebody let me know. I think those were the errors. Okay, short answer, while loop. Sentinel-based while loop. This was pretty straightforward. Most people pretty much got this one. Write a Sentinel-based. That just means wait until, see if the user enters 0.0. Now, a number of people figured out very nicely that you could convert the input to float, but because of what I gave you in instructions, you actually didn't have to. You could just compare the string. The one thing I did need to see is you had to set the value of the deposit amount before you went into the while loop. You could use a priming read. So in other words, you could prompt for a first value and then check, or you could set the value to something that was not 0 explicitly. What you could not do is just give me code where you said while deposit amount's not equal to 0.0 and it wasn't defined, it wasn't set. You needed to set this deposit amount. You can either use a priming read, which is the best strategy. You could set it, which was okay, got you full credit. You could convert everything to floating and compare numbers to numbers. You could leave the input as a string and compare to the string 00. That would work. Either one. This one, 13, really just showed me that you knew split and join. The bottom line here is if you take this string, this initial string, and split it on a comma, now you have a list, and then you use a plus sign. It's quote plus join the list that you've got, and that'll give it back. So really 2 statements, or you could do it in one. Split it on the comma, join it with a plus, and you're done. If you did something more complicated, okay, if it worked and gave you credit. But it was just show me that you understand that split takes this string and makes it a list, and join puts that list back together with these. Difference between a parameter and an argument, I got all kinds of different answers, but mostly people got it right. The argument is the value in the main program or in the calling routine that's going to be passed. The parameter is what's defined in the function, and it's where the value is going to be stored when it's passed. The key things I was looking for are parameters of the function, arguments of the calling routine, and the value is going to be passed from the argument to the parameter. And if you got that, you're good. Okay. 15. Given this list of states, write a for loop that prints out each state's name if and only if the state's name ends with A, E, I, O, or U. The easiest thing to do was write a loop that said, remember, the last character in any string is -1. So say for state in states, and if state sub -1, which is the last letter in the string, just compare that last letter in the string to A, to E, to I, to O, or to U. I tried to be generous with the partial credit. If you made a good shot at it, I don't think you got worse than about 6 on this one. And most people got it right, except for a minor error here or there. The biggest thing was overthinking this one. This, it really wasn't that complex. And if you went down the wrong path, you could have a problem, but it was fairly straightforward. 16 was the same string. Write code that creates a 2D list of states with 5 rows and 10 columns. Most people did pretty well here. The thing to remember, we did one fairly much like this in class back before we had to stop going to class. Build a row. In other words, go through this single list and take one state at a time and append it to a list. Now we have 10 states. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. After Georgia, take that row and append it to your master 2D list. Then go back and build the next row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Up through Maryland. Then add that row. Like I said, I was pleased. Most people did pretty well with this. The key was to understand that because you can deal with a row at a time, you take 10 states, you build a row, then you append that row to the 2D list, and you're good to go. Now, 17, again, I tried to be generous with the partial credit. If you made a really good shot at it, I don't think you got less than 12 or 13. I give you a file of 10 cities in Louisiana, well, cities or towns or villages, with their population, no punctuation, no blank spaces in city names, no commas in populations, just whatever. Here is a town with its population. 3 of those cities on that list I used to live in. We won't go into that. Any rate, what you have is a function that reads this file in and converts it to a 2D list. That's fairly straightforward. Read in each line, and for each line, split, it comes in as a string, split it into the 2 elements of the list, and then you're good to go. Now, in this one, to do the comparison with the largest population and the smallest population, you do need to convert this population into an integer. That's why I didn't put any commas in it, because it's easier to convert this into an integer than 389,648. So the first thing you do is you read it in line by line. Use the read statement and read the whole thing that I looked at how you split it, but that's fine. Read in a line, split it into 2, this element and that element, convert this into an integer. I told you, you may use the built-in sort method in your code to sort it in order, and then all you do is print out the name of the city with the largest population and its population. So all I really wanted to see was you print out New Orleans and this population. That was the only thing you had to do. If you made a good shot at it, that was fine. Like I said, I tried to be generous with the partial credit. Number of people, sort by definition sorts into smallest to largest. So a number of people lost 1 point because if you just sorted this, it's going to put the smallest town, which is Point de la Hache, which is down at the end of the Mississippi River, as the first element in the list, and that's not what you want. So if you sorted and you either had to use sort reverse equals true, so it gives you the largest to smallest, or you had to sort and then print the last value in the list. So that was all I wanted to talk about in the test. If you have specific questions on your specific grade or whatever, and I know a number of you I've already talked to, if you have more specific questions, let me know, and I'll try to explain privately why I took this many points off or what happened. If I made a mistake and gave you too many points, I don't want to hear about it. If I made a mistake and cost you points, took off points unfairly, ping me after class and we can talk about it that way. But that was the test, and those were the answers I was looking for. And as I said, overall, I was pleased with the results. Now, that being said, I want to turn to Project 2. Since, going back to the slide, Project 2 is out. Let's talk about it. Project 2 is available on Blackboard. Down here, it is also available on GitHub. I made a new repo, Spring 2020 Project 2, for this project and the data files. I'll be putting some more stuff out there in the next day or so. What I'm going to do is give you a list of test cases for you to make sure your project works. But let's go through it. Go through Project 2. The goal of Project 2 is to show me you can work with 2D lists. As with the other projects, it's worth 80 points, 10 for your design, and the others for the code, compliance with standards, documentation, comments, and correctness. What you're going to do, I do not give you a whole bunch of functions. I do not give you constraints. I'm going to let you express your freedom, but you have to be properly modular. have to write functions. Okay. If you do something multiple times, it should be a function. You do something separate from the rest of the code, put in a function. If you need to interact with the user in a system in different parts of the program, that's a helper function. Make sure you have enough functions. You're going to reuse 2 of the data files from project 1. So you already should have these 2 files. You're going to be using the fall 2020 and the spring 2021. So you do not have to worry about spring 2022. That was the one with all the funky extra blank lines. Not going to be a problem. You're just going to use fall 2020 and spring 2021, which should be straightforward. There's student grade records from future classes. That way don't violate any student privacy. Each file contains the 2 header lines, which you don't need, so you'll read in those 2 header lines and discard them. After that, you have a different number in each file of student records, 1 record per line. And again, as a reminder, on each line, you have a student last name, a student first name, a student ID, project 1 grade, project 2 grade, project 3 grade, test 1 grade, test 2 grade, and test 3 grade. It's a CSV file, so every value is separated by a comma from the next value. Okay, so you'll read in these things, and you have to split them by commas. Step 1, read them in, process them. Create a 2D list for fall 2020. Create a separate 2D list for spring 2021. That'll be important later on when you're searching for a specific student record. You will put 1 student record per row in your 2D list, and you must have exactly this format initially. The first column, column 0, remember we always start counting from 0, is going to be a string that has the student's last name. Column 1 has a string that's the student's first name, and column 2 has a string that's the student ID. The other 6 columns, 3 through 8, are going to be integers, and they're the scores on the various assignments, projects, and tests. Okay, these are all integers, so you have to convert them from strings to integers. Now, when you have successfully built these 2 2D lists, now you can move on. Okay, so build these first, test it, make sure you've got this data in exactly this format, then you can move on. Now, step 2, you're going to demonstrate mastery of 2D lists by inserting 3 new columns. The first goes in the middle. I want you to prove you can insert a new column 6, which is an integer, which is the sum of the 3 project scores. So when you insert, now of course, if you do it right, Python will automatically move the previous columns 6, 7, and 8 over. They will now become columns 7, 8, and 9. And that will make room for this new column. So you put a sum of the students' 3 project scores. Get that done. Now you add a new column 10, which is an integer, which is your the student's total score. It's the sum of columns 6, 7, 8, and 9. The new 6, the new 7, the new 8, the new 9. You do not add a column for the sum of the 3 test scores. You don't need those. I could have had you do them, but you've already demonstrated that you can insert such a column. So why have you do it again? Insert 6 and then append 10, which is your total score. Now you're going to calculate the student's letter grade and put that in column 11. So you're going to put a new column 11 into each 2D list. That's the student's letter grade. The total possible points is 640. I'm telling you that. That's the total possible. That should probably be in your program as a constant. That would be a hint. Max points or total points or something like that. Should probably be a constant. To calculate the letter grade, take what you put in column 10, the total points, and divide that by 640. Okay, and we're just doing the straight 90%, 80% cutoff. If column 10 divided by 640 is greater than 90%, greater or equal to 90%, enter an A in column 11. If it's greater than or equal to 80% but less than 90, put a B in column 11. Similarly, put a C, D, or E in C, D, or F in column 11. Okay. So now, when you're done this, you have 2 2D lists with 11 columns in each. If that all works correctly and it looks perfectly to you when you print it out, when you display it on the screen, move on to the next step. Now you're ready to go to step 3, which is the start of your providing a database to a user. This is a student grade database that somebody can query to decide what grade this student got. You're going to provide that interface. Your basic interface is a menu. The menu, like I said, you do not have to look exactly like this, but it should be very similar. You should give the users these exact choices. Okay, you can have different words. If you think you're more poetic than me, you're probably correct. You can give better messages and guidance and instructions. That's fine, but it better work pretty much the same as this. A welcome message. Welcome to Student Grade Information System. What would you like to do? Now give the user a menu. To search by student last name, enter an L. To search by student ID, enter an S. To exit the system, enter a Q, and then read in the user what the user types. Now, your program can't crash here no matter what the user types. That's a rule. And the reason it works this way is because since all inputs a string, you're going to input a string, you're going to read a string. There's no reason your program should ever crash you. Even if the user types the number 1 or 93.5 or 3.14, no crashing allowed. We will be a little forgiving of the user here. We're not going to care if the user types an uppercase or lowercase letter. L, upper, lower, S, upper, lower, Q, upper letter. It should work the same. That's a hint to you that you're either going to have to use the upper method or the lower method to convert. That's fine. Okay, if the user types a Q, you go straight to step 8, where the program terminates. If the user enters anything other than the 6 values listed above, upper lower Q, upper lower S, upper lower L, then you display an error message, echo the user input, and says, I'm sorry, but that's not a valid choice. Okay. So in my little angle brackets, in my less than and greater than sign, it says echo the user input. You'll print what the user actually typed there. And then redisplay the menu, keep doing this until the user enters a valid value. Okay, aha. That seems to be a hint that in this function that's going to implement step 3, we've got a while loop that continues until the user implements something valid. Now, step 4. Okay, if the user typed a Q, quit, we said go to step 8. So the fact that we got to step 4 says the user either entered an L or an S. The user's going to search for last name or student ID. But before the user searches, we need to know which semester. Remember, we had 2 different lists, fall and spring. So we're going to ask the user, what list should I search? F for fall, S for spring, and U for I do not know. Again, no excuse for crashing. If the user enters a weird value, simply print an error message. Using the same method you displayed in step 3, so it sounds like maybe there's a helper function that prints error messages. That's a hint. And redisplay the menu and keep doing this until you get a valid input. When you have a valid input, go on to step 5. Now, here's where we fork. Here's where we split off. If the user was in step, if the user said, I want to search by last name, I need to go to step 6. Passing the value you got in step 4. In other words, I'm going to step 6 and I'm going to say either search fall, search spring, or the user didn't know. We'll get to what happens there in a minute. If the input in step 3 was search by student ID, go to step 7. Again, which semester you're going to search. All right, now we are in step 6. We are in some function. It's a function that processes a search by last name. Ask the user to enter the full last name of the student for whom the user is searching. The user is going to enter a string that we will search for. Okay. Here's the deal. If the user said F for fall, only search in the 2D list for fall 2020. Only search there. If the user entered spring, S, only search in your spring 2D list. Okay, user said fall, only search fall. User said spring, only search spring. But we're going to be nice. If the user said, I don't know what semester, search all semesters, you are potentially going to have to search both lists for a match of the last day. The user said you'll search both lists. But the reason we had you keep these two files, these two things separate, is it narrows the search in some cases. The next instruction says, match whatever the case is, be nice to the user. So again, that's a hint that you're going to use either the upper or lower, it doesn't matter, method to compare strings to match. Now, a couple of cases, edge cases, our code has to deal with. The first is an error. That user was not in that course that semester. There's no match. If the user typed it wrong, somebody misspelled Rostenkowski -Wolowitz. That's possible. Let the user know what you typed is not there, not full. Please enter a valid last name. Now here, when the user says Q to quit, the user says, I want to go back to the main menu, not exit the program. So here, we're going back to the main menu, not the program. The other edge case says, we've got more than one student with the last name, same last name. We've got a couple of students named Cooper. We've got a couple of students named Hofstadter. If the last name matches more than once in the list, you have to ask the user to choose among the matches. And so you're going to display an error message that says, a message that says, which one of these students do you want? You said Cooper, which one do you want? Here, don't worry about validating input. Let's presume the user can correctly enter a 1 or a 2. Or a 3. I think there's one case where there's 3 with the last name. I'll have to go back and look at the data. What you're going to print for the correct student, for the matching student, is you're going to give a header row, last name, first name, ID. Don't have to worry the individual grades, total points, and letter grade. And so you're going to print the values from column 0, 1, 2, 10, and 11 for the matching record. This is what you're going to pad. This is what you're going to print for the match. Once the valid record's displayed, you go back to step 3. Step 7 is the same as 6, except you're searching for student ID, not student last name. And here there is only one possible match. So in step 7, when you're processing searches for student ID numbers, you do not have to worry about matching multiple students, just one. So, but the logic is pretty much the same. You're just searching in a different column. If there's not a match, you tell the user there wasn't a match, and you ask them to try again. Q to go to the main menu. Print out the same information. And then lastly, but not leastly, step 8, exit the program. The user has chosen to quit the program, so print out a farewell message. Don't die a horrible screaming death. I very nicely print out a farewell message similar to the following. Again, if you're more poetic than I am, hey, have a better farewell message, but give something that says, we're shutting down now, you're done. That is project 2. It's, to me, in many ways, simpler than project 1. It's more straightforward. Okay. You're reading in these 2 data files, which I've put copies of in the GitHub page. I've put copies of the data files on Blackboard. You already have them, so you should not have to fetch them from anywhere. But if you do, you have 2 places you can get them from. You need them on GL. You should have them already in GL. Okay. That is project 2 description. In the next day or so, when I get a chance, I will give you a set of test cases that you should be able to run and get results. I'll give you test cases where you should fail. In other words, the student's not found. I'll give you test cases where you should pick between 1 of 2 students. I'll give you test cases where there's only one answer. This is similar to what the TAs use when they grade your project. So you'll have some idea there. That is project 2. Okay. So I've been doing a lot of talking and I've rushed through this. Are there any questions on Project 2, or if somebody want to say something about the exam before I move on? Okay, I'll keep going. As I mentioned, the next bullet is a lie. It says Lab 8's released tonight. It actually was released a few minutes before class. It will be due Thursday by midnight. It is on Recursion, so it is actually going to be in the material we'll cover tonight and Wednesday. But it's fairly straightforward. I'll walk through it for you real quick right now, and then we'll get into the lecture so you can start to understand how this works. Okay, it is on, the Lab 8 is on GitHub. I don't think I put it on Blackboard yet. I can if people really want it there, but it's available on GitHub. So, gravity. We discovered a whole new planet. It's got strange gravity. If I have a hailstone that's above the ground, it will not always fall to the ground accelerating at 32 feet per second squared. It's always an even number of feet away from the ground. If it's within a foot of the ground, 1 foot above, it falls to the ground immediately. It takes no time. If it's an even number of feet above the ground, it falls half the distance per time unit. Every second, every minute, whatever your time unit is, it falls half the distance to the ground. If it's an odd number of feet above the ground, it's actually going to rise. I told you it was strange gravity. The hailstone will rise during the next time unit. It's in the new time unit, it's 3 times as high as it was plus 1 foot. The reason we do 3 times plus 1 is that guarantees to give us an even number. Any odd number times 3 plus 1 has to be even. So that will guarantee that this thing is eventually going to fall to the ground. There is no infinite loop. You're going to write a program that determines how long, how many steps, how many units of time it's going to take an object starting at any height to hit the ground, and you must do it as a recursive function. Now, the next text I'm going to skip because it's stuff we're going to talk about in today's lecture. It's how recursion works. It just gives you more examples.
Quick question.
Question? Yeah, Greta.
Yes, about the first question. So are we just assuming that we're only looking at the stuff between the jumps, basically, per time unit? Or are we looking at it in between? Because, like, in between, like, say it's at 10 feet, at 10 feet, and then it's going to go to 5. But before it gets to 5, it's going to have to cross 9. So does it turn? Or even 9.6 or 9.7?
Right. Great question. And the answer is you only look at even time units. So as far as you're concerned, if it's at 10, it immediately jumps to 5 in 1 unit. And you don't have to worry about the fact that it went through 9, 8, 7, and 6 to get there. It just goes straight from 10 to 5, and you don't worry about anything else.
All right. Thank you.
All right. So I will show you what this file looks like in a second. I've tried to make things easier for you. In my public directory on GL, I have a file called hailstone.py, which you should be able to copy directly to your GL account using this copy statement that I've given you, cp/afs/umbc.edu/users/arrs/home pub hailstone.py, and then this copies it to a file called hailstone.py in your files. So you shouldn't have to SCP, you shouldn't have to get it from GitHub or Blackboard or anything else. You should just be able to copy this file, hailstone.py. Now, what this thing looks like, let me see if I can share. Share a terminal. Okay. This is what you will be copying. It is the skeleton of a Python program. And I'll highlight it to make it clearer in this hideous terminal thing. Let me see if I can make this bigger. A little bit. Okay, what you will be copying is this program, which consists of one function and a main. I have given you the fact that the function is called flight, and it takes one parameter, which I called height, which is an integer. If you go through the program, you figure out it's an integer. And then I've given you comments that tells you what this function does. It calculates how many steps it's going to take for an object, a hailstone, falls to the ground on the strange new planet. So what I need you to do is first write the base case code. What's a base case? We're going to cover that. What happens if it's 1 foot or less from the ground? If height is less than or equal to 1, return, and here's a comment, you're going to have to complete the return statement. Okay? Now there's an elif because there are 2 recursive cases in this lab. You have to write the code for each of them. They are the height's an even number and the height's an odd number. So I put in a skeleton, says, what makes a number even? You're going to have to give me an if statement that says if height is something that makes it even, then what do you do for an even number? What should you return? You're going to call another function. You're going to return a value. Here, if it's not even, it's odd. And so you don't test anything. It's odd. It's an integer. You just come down here. What do you do for an odd number? You're going to write this code. Okay, again, we're going to cover this afternoon, so no big deal. I won't expect you to know what I'm talking about right now. This is what you're going to do. And then I give you the main program. I tell you, prompt the user to enter the input in height, the height in feet of the hailstone, and convert it into an integer. This is your input statement. Take in what the user types, convert it to an int. Don't worry about input validation. We'll presume the user's going to type a real integer here. This is just a lab, not a major project. Now you make a call to the function right here. I gave you a parameter. You're going to have to figure out what the argument is. And you're going to call this function. When the function returns, the value that it returns is going to be stored in this value steps. And that will mean you can print out a result with this print statement. Okay. So that is the file that you're going to copy right here with this copy statement. What I need you to do in the lab is look at the code for that function and for the main program. Make sure you understand what's going on. Make sure you understand those comments. The flight function does this. Here are the rules for the base cases, and here's the rule for 1 foot or less. Here's the rule for if it's even. And here's the rule for it's odd. So that tells you what code. That's the pseudocode that's going to drive the code you're going to write. You must do this as a recursive function. Yeah, I know you could do this with a loop. I don't want you. You've already proven to me you can write loops. I know you can write loops. Move on. Do it recursively. Write the base case and the 2 recursive codes. Test values I want you to use. These should be the correct outputs. If the user inputs -4, you should get a result of 0 steps. If the user inputs 1, you should get a result of 0 steps. If the user inputs 16, you should get a result of 4. Because it's going to go from 16 feet to 8 to 4 to 2, and then 1 gives you another 0, so it's 4. If the user inputs 9, it's going to take you 19. If the user inputs 30, it's going to take you 18. If the user inputs 13, it's going to take you 9. And if the user inputs 64, it's going to take 6. If your response gives you if your program gives you the correct answer for all 7 of these values, you can be pretty darn sure your program's correct. Now, if anybody finds an error in my test values, let me know and I'll go back and redebug my code. But I'm pretty sure that's correct. So that's what you're going to do with the lab. You're going to copy that file from my public folder on GL, so you don't have to SCP it. You don't have to get it from GitHub, anywhere else. It's already on GL. Copy it, and put it in Emacs, edit it, write the code, test it out. Make sure you get the right answers. That's due Thursday night at midnight, and submission should be open today, I hope. I asked Monolith to do that. Should be dead set. So, Project 2 is out. Lab 8 is out now. You have till Thursday night. Hopefully after today's lecture, and if necessary after Wednesday's, you'll be good to go on that. Homework 6, don't worry about. The original schedule said it was out this week. It's not. It's going to be out next week. You don't have to worry about it at all this week. Okay. Last thing before I actually get to talking about recursion. Changes to the schedule to reflect the fact that we're doing this online, to reflect where we are, and to reflect my judgment of what's valuable for you to take out of this course. Here's what we're doing the rest of the time. This week, we're talking about recursion. Today and Wednesday, recursion is the topic. Lab 8's out and Project 2 Start is out. Next week, April 20th and 22nd, I'm going to make a departure from the course for the majors. The course for the majors kind of assumes that all the students will eventually be professional programmers. They'll write code for a living, and they need to learn tools that professional programmers who write sections of code for big applications need to use. Things like Django, things like Flask, things like other stuff. I'm going to assume your main interest is not how to get a job as a professional programmer. Your main interest will be to learn how to use Python in your academic and professional careers to get a job done. Therefore, I will talk next week about, first, a Python tool that you could use to write term papers, research papers, professional publications, and everything else through your career. It's called Jupyter Notebooks, often pronounced Jupyter, spelled Jupyter. It's a way of using Python and possibly other languages to present results with Python code embedded that can be executed at will to show how you derived your results. The other thing I will talk about next week is graphics. Python has a really cool library called ggplot, and we will use the ggplot library to do great data visualizations, great graphics, great charts, bar charts, all these other fun things you can do that might help you the rest of your time in college and then out in your career, your really cool research and application results using Python. That will be the topic of Project 3, so I'm going to cover it in class next week. We will also do Lab 9 next week. You'll have Homework 6 and the end of Project 2, so it's going to be a busy week for you, so get a jump this week. The following week, 27, 29 of April, I will return to the real topics of computer science, and we will talk about binary numbers, long strings of ones and zeros, hexadecimal numbers, everything's base 16. I'll talk about algorithms for sorting and searching. That's when Project 3 will be released. You have next week to learn the material before we start on the project. The last full week of class, May 4th and 6th, will follow up computer science with analyzing algorithms, looking at all those sorting and searching techniques and how fast they are and which ones are better. Algorithmic complexity, and you'll have Lab 11 then. And then the last class on the schedule is Monday, May 11th. It is intended to be just a review for the final. And that's the day Project 3 will be due. So that's what the rest of the semester looks like, updated, taking into account that we are all working from home doing this online. So that's how I've changed the schedule and the content, and that's what we're going to do. That being said, let's finally, with half an hour or a little less left in the class period, let's talk about recursion. Python functions. We mentioned earlier, a function can be anywhere in a program except on the left-hand side of an assignment statement. You don't have to define functions before the main program. Functions can come before the code that calls them. Functions can come after the code that calls them. Functions can be inside of other functions. Don't do that in this class, but they can be. Functions can even call themselves. Functions can call themselves. Why on earth would you do that? And isn't that going to be an infinite loop? You're going to keep calling a function from itself, and it's never going to end. Well, the answer is that can be dangerous, and you can cause infinite loops real quick, and you can crash computers and run out of resources. it is sometimes useful to have a function call itself. When a function calls itself, that's recursion or recursive programming. And it turns out to be a very useful way to solve certain problems because it's a very easy way to understand how things work. When certain things have to be done over and over with slight differences that can simplify, sometimes recursion or recursive programming is the best way to go. Up until now, when we used loops, for loops and while loops, that's called iteration or iterative programming. So we've done iteration, and we've done iteration to death. Now we have another thing here that just with loops, just like with loops, everything you can do one way, you can do another way. Anything you can do with recursion, you can do with iteration. You never have to have recursion. You can go through your whole life doing everything iteratively and it will work. It may be doggone ugly. It may be hideously ugly. It may be horribly complex, but you can do it with iteration. So why do we use it? Why do we do recursion? Because sometimes it's just easier to solve that way. How does recursion work? Logically, think about it this way. I give you an assignment. The assignment I'm going to give you is run over there and bring me my laptop, which is 10 miles away. I left my laptop in my office on campus. I live 10 miles away. Run 10 miles, get my laptop, and run 10 miles back to me. Now, if a task is easy enough, you just do it yourself. If you're in shape, if you're an Olympic marathoner, if you're Des Linden or Galen Rupp or somebody like that, hey, you're going to run the 10 miles yourself and get me the laptop and run the 10 miles back. Okay, fine. That's called the base case. Do the task yourself. But for most people, that task is kind of too hard to do directly. So you come up with an idea. I'll do part of the task. I'll do it a little bit, but I'll get somebody else to do the rest of it for me. And this is where we get into the recursive case. This is where we go into recursion. Okay, you're going to do work. I ask you, run 10 miles, get my laptop, run 10 miles back with me. You're going to do part of it, and then you're going to get somebody else to do the rest of it. Now, the note on the bottom is this is only going to work if you actually do part of the task yourself and you get other people to do a simpler version of the task. I ask you to run 10 miles each way, uphill and this and up. You don't want to run 10 miles each way. So you turn to your classmate and you ask her, hey, can you run 10 miles and get Arsenal's laptop? Well, she doesn't want to run 10 miles either. So she turns to the person sitting next to her and goes, can you run 10 miles and get Arsenal's laptop? This is not going to work. We're going to be in an infinite loop because unless you can find a marathoner, nobody wants to run 10 miles each way. Nobody's willing. So how this works is you have to give that person a simpler version of the task. I ask you to run 10 miles. You say, I'll run 1 mile. I'll ask somebody else to run 9. You give them a simpler version of the task. They may be a little more willing until we get down to the end. So my new laptop's in. It's over at UMBC. I can't go to UMBC. Bring it to me. It's 10 miles away. You have to go on foot and carry it uphill through the snow each way. You don't want to do that. But if we're doing this iteratively with a loop, that's what you're doing. Your iterative solution is you run a mile. Then you run another mile. Then you run another mile. You keep doing this until you've run all 10 miles. You pick up my laptop. Come back a mile. Run another mile. Run another mile. Keep doing this until you brought me back my new laptop. Woo! I get my laptop. It's a lot of work for you. It would work iteratively. This is a reasonable solution. It can be done. But it's a lot of work for you. You don't want to do that. You offer to go 1 mile. Then you ask somebody else to go get the laptop, which is now 9 miles away. She goes a mile. She asks somebody else to get a laptop 8 miles away. That person goes a mile, says, give me a laptop 7 miles away. This repeats until somebody is asked to go get a laptop only 1 mile away. This is a person who's just off campus. That person is willing to go onto campus, into the ITE building, get my laptop, and bring it back 1 mile to the person who asked. That's reasonable. That's the base case. That's a task you can do by yourself. Okay. Then everybody else brings the computer back the 1 mile they came. I got my computer. It's a win. Nobody had to run 20 miles round trip. Another win. Nobody had to go more than 2 miles. Another win. We could solve the problem iteratively. Hey, you run 20 miles, or we could solve the problem recursively. Each of you does a little bit and passes on a simpler version of the program. Hokey example, I know. It's lame, but that's okay. It illustrates the point. The base case in the recursion was the last person. That person agreed that this task is easy enough. I'm just off campus. I got to go a mile, get the laptop out of the ITE building, come back a mile. That's not too hard. I can do that task. The base case was the person who said, I can do this all myself. And she just did it. Everybody else is part of the recursive case. Everybody made the problem a little simpler, and then everybody got somebody else to do it. Now, if each person didn't make the problem a little simpler, get a little closer to the laptop, this wasn't going to work. If I asked you to go 10, and you asked your friend to go 10, and she asked her friend to go 10, we're never going to get my computer, and I'm going to be darn unhappy. So you each have to make the problem a little simpler. So conceptually, recursion. Everybody does a little bit, makes the problem a little easier, and passes it on till somebody finally says, this is easy enough, I'll just do the darn problem myself. I mean, you know, but again, a fake. It's a lame example, right? You have to have friends who happen to be 1 mile closer to the computer than you are, and they have to be willing to help out. What are the odds of that happening in real life? I mean, it just ain't going to happen, right? But what if those friends are not really friends, but they're clones? They're copies of you. What if those people are copies of you? So they're guaranteed to help you out because they are you. And what if by you, instead of a carbon-based life form, we mean a software function that can clone copies of itself at will? It's a function. It can call itself, create a clone. It can call itself, create a clone. It can call itself, create a clone. Now we're getting into an example that's not really all that hokey because we've always got these friends to help us out and do the project and make sure we succeed. And that's what's going on with recursive programming in Python is we're creating clones. We're creating functions that will help us solve the problem. Mathematically, I think you all know how to compute a factorial. In fact, we did this iteratively earlier in the semester, back when we were in the interdisciplinary life sciences building. We did this. N factorial, or n exclamation point, positive integer, is just the product of all the integers from n down to 1. N times n minus 2 times n minus 1 times n minus 2 times n minus 3 all the way down to 1. Iteratively, we can write a function to calculate the function, to calculate factorial, and we do it on the left side. The product, we start by creating the product equal to 1, and then we write a loop, a for loop, and we could do this either up or down, but I've chosen to do it down, so I start with n, and I multiply by n minus 1, n minus 2, until I'm done. I can multiply by 1, I don't have to. The way I've written this iterative function on this slide, I actually don't multiply by the last one, but hey, who cares? Because multiplying by 1 gives me 1, gives you the same result. Now, on the right, I have a recursive version of this same function, which says if n equals 1, that's my base case. 1 factorial, by definition, is 1, so I return 1. Otherwise, I return n times n minus 1 factorial. Now, what I'm going to do, rather than showing you this in PyCharm, is I'm going to go to a website. The link is on this slide. If you follow that link, you get to this website. It's called pythontutor.com/visualize, and it's going to help us visualize how recursive programming actually works, okay? So this is the factorial function I've written. It's from the slide. I've copied it in to this place where I'm using Python. This site has not updated from 3.6, but fortunately 3.6 works the same. And I'm going to calculate 5 factorial. So I'm calling my function with 5 factorial. Now I'll click on this little box that says visualize execution, and it will take me to what did I do now? Oh, I capitalized the I in if, which makes it a syntax error, and now I fixed it. Okay. Knew I was going to have a problem with that. Okay, you can close. I don't want to. Let's see if I can make this bigger. Okay. This should work, I hope. Here on the left is my function with the call to factorial 5. The Python interpreter thinks it's executing the statement where the arrow is. So I'll say execute that statement. It says, this is just a function. Let's go to the main program. I'll go down here and say, I will execute the statement factorial of 5. On the right, we can see that it has created a copy of factorial, and it says, I am now going to call factorial of n with 5. So it creates a copy of the function factorial, and n here is 5. Argument 5, parameter n now has the value 5, and this Python will now execute this function with n equals 5. So Python says if n equals 1, well, n is 5. So that obviously is going to fail. So what's going to happen? We go down and we say return n times factorial of n minus 1. Remember, n is 5. So what happens next? We have to execute this right here. Fact of n minus 1 is the 4 factorial, and it says we create a new function of factorial with n equals 4. Now, the point of visualizing this, the point of doing what I'm doing and going through these steps is to show you that I had my global, my main program is executing, it called factorial, it's waiting for factorial to return. I called factorial with n equals 5, that's still there, that's still alive. N equals 5, that has not ended, it's still waiting, it just called another instance of itself, and so now I'm executing factorial with n equals 4. This is still alive, waiting for a return. This is still alive, waiting for a return. Now, in n equals 4, I'm coming down, I'm executing if n equals 1 in this function. N equals 1. No, n equals 4. So I'm going to come down to this next statement. N times factorial, and n minus 1 is going to be 3. So what am I going to have to do? I'm going to have to create another copy of factorial, right? I cleared another copy of factorial, n equals 3. What am I doing? I'm creating clones of myself with a slightly simpler problem. This is the base case if n equals 1. This is the recursive case, the else, return n times factorial of n minus 1. My recursive case made the problem simpler. I started by calculating 5 factorial. Now I'm calculating 4 factorial. Now I'm calculating 3 factorial. When I step through this, 3 is still not equal to 1. I'm going to come down here. I'm going to have to calculate 2 factorial. So now I'm calculating 2 factorial. Is n equal to 1? No, it is equal to 2. Come down here. Return n times 2 minus 1 is 1, so now I'm going to calculate 1 factorial. Okay? So here, what am I illustrating? My main program called the global frame is running. It's waiting for something to return. Factorial of 5 is running. It's waiting for something to return. Factorial of 4 is running. It's waiting for something to return. Factorial 3 is running. Factorial 2 is running. I'm actively executing factorial 1. 1 factorial, all these other functions, they're just functions, they're clones of myself, they're recursive functions, they're waiting for something to return. Now, 1 factorial. Sorry, knew I shouldn't have jumped there. All right, what do I do now? It figures. All right. Now, 1 factorial. If n equals 1, yes, n equals 1. So what am I going to do? I'm going to return 1. So n factorial of n of 1 is going to return 1. And then this function is going to terminate. When that function terminates, I come back into 2 factorial. Well, what was 2 factorial? It's 2 times 1 factorial. 1 factorial was 1. So I'm going to return 2. And now that I can return 2, this function is going to terminate. And now I'm back in the 3. And 3 is 3 times 2 factorial. That's just 3 times 2, which is 6. So this is going to return with 6. What is 4 going to return? Well, 3 factorial right here was 6. So it's going to return 4 times 3 factorial. 4 times 6 is 24. So 4 factorial is going to return 24. Finally, I'm back to 5 factorial. 4 factorial was 24. We just got the return value. 24 times 5 is 120. 5 factorial is going to return 120. And now we are finally done. Okay, so hopefully that made sense. What I did there was show you what happens in the computer when this code runs. When I called this code with 5, that's what happened. It called the function. The base case was not true, so it recursively called itself. With 4, the base case was not true. It recursively called itself with 3. The base case was not true. It recursively called itself with 2. The base case was not true. It called itself with 1. Now, when I called with 1, here's a task that's simple enough for somebody to do. Somebody's got the answer. The answer's 1. Now we can return, and each of those returns gives us the answer to that recursive problem. So understand recursion is confusing. I had a lot of trouble when I first started with it back in the dark ages. But it is a process where you call clones, additional copies of yourself, with slightly smaller values, with slightly simpler things, and now you can eventually get to solve the problem. So that slide simply illustrated it. Because we're running low on time, I'm not going to walk through this today. I'll do this on Wednesday. But here's another example. You have the Fibonacci sequence, which hopefully most of you have heard about. It's very famous in mathematics, has a number of applications. The Fibonacci sequence is 1, 1, 2, 3, 5. The rule is the first 2 numbers in the Fibonacci sequence are 1 and 1. Every succeeding number is the sum of the previous 2. 1 plus 1, that gives you 2. 1 plus 2, that gives you 3. 2 plus 3, that gives you 5. 3 plus 5, that gives you 8. 5 plus 8 gives you 13, and you follow on to infinity. This is called the Fibonacci sequence. So how would you write a computer program or a function to find the numbers of the Fibonacci sequence, the nth number in the Fibonacci sequence? Well, we know the nth number is the n minus first number plus the n minus second number. Those are the 2 numbers that go into it. As you can see, the iterative, it's bigger. The The iterative code to implement the Fibonacci sequence is kind of a pain in the neck. If n is less than or equal to 3, return n. Okay. The reason I do this is because it's a list, and this is actually 0. Again. 0, 1, 2, 3, and so on. That's why this n is less than or equal to 3, return n. Otherwise, start by creating a list whose elements are 1 and 1. Go through and calculate every one this way. This is using a for loop to calculate the Fibonacci numbers and return it. So that's kind of a pain, but it works. That gives you the correct answer to any Fibonacci number. The nth, you'll always get it. Recursively, if n is less than 3, return 1, else return a recursive call to n minus 1 plus a recursive call to n minus 2, and you're done. And if you want to play with the Python tutor routine again, you can visualize all the calls to the recursive function in the Fibonacci routine. We'll talk about that again in detail on Wednesday. I just wanted to go through it. Getting back to the lab, because we've now covered an intro to recursion. You need a base case and a recursive case. That's what this text in the lab, this background, is another way of saying what I just did. I have a base case and a recursive case. It's a conditional. It's simple. In our lab, there's some more code that's an example of how to do it, and hopefully that will explain more if you want to. In our code, the base case is this. If the height of the hailstone is 1 foot or less, it will hit the ground immediately. It takes 0 steps to hit the ground. That is our base case in the lab. If the hailstone is 1 foot, your program can actually take a negative number. A negative number is one of the test cases I gave you. It's on the ground immediately. There are 0 steps. We're done. So that is the base case in the lab. Now, in the lab, there are 2 recursive cases. A recursive case, we're going to call it with something simpler and smaller. Here is a recursive case. If it's an even number of feet above the ground, it falls half the distance. That means we simply say that it takes one more step plus the number it takes to fall half the distance. Let me see if I can make that clear. That was not clear at all. That was lousy. Suppose the hailstone is 16 feet above the ground. In one time unit, in one step, it will fall to 8. Now, how many did it take to fall 16 to the ground? It takes 1 plus the number it takes to fall to 8, from 8. How many did it take to fall from 8? From 8 in 1 unit, it will fall 4 to 4. From 4, it will fall to 2. From 2, it will fall to 1. And then from 1, we know it gets to 0. So what we're setting up here with B, with the part of the lab that I have highlighted right now, is you're going to make a recursive call to the function, to the flight function, with half the height. And you will add 1 to the result. So in other words, how long did it take to fall from 16? Well, 1 time unit plus what it took to fall from 8. So this case in the lab is going to be a recursive case. It's going to be 1 plus a recursive call to flight of half of it. This one is a little more complex. You could argue I haven't simplified the problem, but it's the same thing, same idea. If the height of the hailstone is an odd number, it's 9. It's actually going to rise. How long does it take to fall from 9? Well, 3 times 9 is 27 plus 1 is 28. So the time unit after 9 is now at 28. So how long does it take to fall from 9? 1 plus however long it took to fall from 28. So with an even number, it's a recursive call to half. And with an odd number, it's a recursive call to 3 times plus 1. So that is how the lab works. The base case is it just takes 0. The recursive cases, it takes 1 plus half or 1 plus 3 times plus 1. And it's a recursive call. If you feel confident enough in that, go ahead and start the lab now. If you'd rather wait until Wednesday and have me explain it some more, you are free to do that. It's not due till Thursday night. There is a lab scheduled tomorrow. Anna will be on Discord from 11:30 to 12:20. Jordan will be on Discord from 4 to 4:50. There will be other TAs available during that time. I understand that there are lots of students in office hours. They're trying to make it a little bit better, make it fairer so everybody gets at least a shot. But if you have questions you want to ask Jordan, you want to ask Anna tomorrow during their office hours, by all means, go ahead and do so. And the submittal for Lab 8 should be open from now until midnight on Thursday. And we are over our time. So are there any last minute questions? Or again, if you want to ask me questions about your test, ping me separately. Let me know when you want to send me a DM on Slack or an email, and I'll set up a time to talk to you. Other than that, we will talk Wednesday about recursion. Anybody? Go ahead. Okay. Have a good day. Talk to you later.